howdy folks. If you've been following along, I don't need to keep doing the introductions, but for those of you at home who want to know about the specific problem, we're talking about chapter 1 out of Koretsky's book. This is problem 1.39. For us, it's homework number 7. So 1.39 states, I have a piston cylinder assembly. So let's draw a piston cylinder. So this is the universal picture for a piston cylinder. Okay, it contains 5 kilograms of water, so mass equals 0.5. Okay, I have water, so water. Okay. At 50 degrees Celsius, and a pressure of 500 kPa, which is half a bar, or rather 5 bars, sorry. Half a megapascal. It is then isobarically, so what does isobarically mean? It means constant pressure. Isobarically heated, so it goes from here, so P1 is equal to P2. Okay, so let's make this T1. Okay, let's see here, until all the water is vaporized. Okay, so who knows where it started, but and all of it's vaporized, meaning all but one droplet. So we're going to assume that the quantity of the final is 100%. Okay, so assume final is saturated. Okay, we're also going to assume that this is a closed system. There's no leaks or anything. Okay. There's no leaks or anything. We're going to assume, well, that was stated, the mass is constant. Okay, let's see. We might need to assume some other things, but let's do that. What is the final temperature and volume? Okay, so, well, the pressure's the same, and we know the quality is 1.0. That seems pretty straightforward. That sounds like a steam table problem. Okay, that's a steam table problem because we have properties and we want to know end properties. Okay, so that's pretty straightforward. Okay, so all we need to do is say what is the final temperature and volume. Now it doesn't say total volume or molar volume or mass volume. Well, we can do both though if we wanted. So let's do both just for funsies because they're most fun, right? That's right. Okay. Alright, so steam table problem, once we've identified it as a steam table problem, okay, let's go to the back of the book to a steam table. And we're looking at the pressure, okay, table. Okay, because the pressure is this thing that stays the constant, and like I said, it's a half a megapascal. So if I go to half, okay, and until all of it's vapor, which is going to happen at saturation, which means the temperature is going to be 151.86 degrees Celsius. Okay? So T final is equal to 151.86 degrees Celsius. Okay? That's a fact. Okay? 0.5. Okay? Because it's saturated. Okay? And even if like that one last droplet vaporized, it'd still be pretty much 1.5. So we're just okay. But again, we assumed it's, we assumed the final state is a saturated vapor based on how it was written. Okay. So we're going to keep up. Now the volume, of course, is we have to actually calculate. So we need to. So the V liquid specific is equal to 0.001093. The specific volume of the vapor is equal to 0.3749. Of course, put in some units in there, but whatever. And I said, okay, obviously I said something about specific volume, total volume, all that good stuff. Well, the specific volume, there it is. It's 0.374. Okay. And let's just, for roundy sake, say it's 0.37. Okay. Now, sig figs, yeah, we can go out more because the table allows us to have those many sig figs. But for the case of this exercise, we're going to keep it that way. Now, what's the total volume? Well, again, we just have to look at the definition of a specific volume, which is the total volume divided by the total mass. And if I know the mass is 0.5, well, the total is equal to the mass times the volume. So half of that is, I don't know, 0.185, but there was that thing, so maybe 0.185 to 7, because there was that 4 in there. Okay. So that's meters cubed. So that's the final volume of the cylinder. Okay. Now you might also want, well, can I find the initial volume? Well, let's think about this. Okay. Can we find the initial volume? Well, I gotta ask myself, does the state postulate apply? Now, what does the state postulate say? It says if I know two independent intensive variables of a system, I know the complete state of that system. So, at the beginning, do I have two independent intensive variables? I have a temperature and a pressure, and because it's not saturated, because it's not at that temperature, I do. So, hey, I could find out the initial total volume. Now I go to this. So, I heated it up to get there, so really I'm a subcooled liquid. Okay. And if I'm a subcooled liquid, unless my pressure is really high, because I don't, let's kind of look at our, I think there's liquid, subcooled liquid. Yeah, that goes at 5, I need 5 megapascals to go to subcooled liquid. So we're going to assume that that's close enough to atmospheric pressure that I can assume this has the same properties as a subcooled liquid. Basically, its volume is 0.001093, and then its total volume is going to be half of that, which is 0.05558, yeah, something like that. No, 549, yeah, 549. Yeah. So, I'm going from 0.000549 to 0.187. So, yeah, I'm basically increasing the volume threefold.